Okay, for this video, we're starting at the bottom of page 7, where we're talking about rotations. And I've already written in for you that a rotation is a spinning motion that turns a figure about a point or a line, and it's a rigid motion. Okay, so we learned that a rigid motion means that it's taking a figure and then moving it in some way and does not change the size or shape of the figure. So it moves a figure to a congruent version of the figure. Okay, so then looking at this, this figure here was turned about a point, and I bet that point's somewhere right about here. And so this is the point that if you were using a compass, that you'd put the stylus, the pointy part of your compass, on that dot and turn. That's why it's going counterclockwise. We would call that point the center of rotation. Okay. And then remember, we would always say the beginning, what you start with is your image or your pre-image, and then where it moves is the image. So we'd say this first one here would be the pre-image, because that's the beginning of the arrow. And then it moves over to here, so this one over here is going to be the image. Okay, the angle that we get for this rotation right here is going to be basically the angle that we get if I connect my center of rotation to any 2 points, corresponding points on our figures or on our images. So if I measure this angle right here, that would be the angle of rotation for the entire figure. Okay, so I want you to pause your figure or your video right now and try these review questions. They go on to the next page, so make sure you answer all 5 of them. Pause your video, start again when you have the answers. Okay, so we're supposed to fill in always, sometimes, or never for each of these questions. The first one says the rotation of the moon about the Earth never takes a year, is what you should have put in. I had to pause the video to go check. It takes the moon 27 days to rotate around the Earth. That's what the full moon cycle is. And a rotation image, it's only sometimes has the same rotation as the pre-image. So rotation would mean like if I have a square, oops, I pushed too hard, and I have this vertex A here, B, C, E. If I rotate it 90 degrees, the A would be here, B, C, D. So it's not the same orientation because the A moved from up here to down here. But if you rotate it all the way around in a circle, it would be 360 degrees. It would have the same orientation. Okay? On the back side, the next question says, a transformation is blank a rotation, while a transformation is sometimes a rotation. There are 4 different kinds of transformations. We have translation, reflection, rotation, and dilation. So sometimes it's a rotation, but a rotation is always a transformation. Okay, last one, a 110 degrees counterclockwise rotation is the blank the same as a 250 degrees clockwise rotation about the same point. So if I did 110 degrees counterclockwise, and let's say we start here, and we have a point here, 110 degrees is kind of like to over here. Okay, pushing too hard. Okay, that's 110 degrees. If I did 250 degrees, if I went to 180, that'd be right here. That'd be a straight line. And I need to go 70 degrees past 180. It would actually go to the same place. And together, it's the whole circle. So 110 plus 250 is 360. So this is going to be always. It will always be the same rotation. Okay, so then we're going to talk about the direction of our rotation, and I've already written in that we can either have a positive angle of rotation or a negative angle of rotation. And somewhere along the lines, mathematicians decided that if you have a positive angle, then you're going to rotate in a counterclockwise direction. Okay, so positive angle means you're going to go counterclockwise. Now, this will be the first time in this class that we've had to deal with negative angles. The angle's still the same. It just means that you're going to rotate in a clockwise direction. So it's going to go this way. So negative angle means clockwise. Okay, and then to go all the way around, so to rotate so that any image would map onto itself, you'd have to do 360 degrees. Okay, so then here's some key ideas with rotations. If you look at this picture here, our center of rotation is right here underneath the R. So I'm going to put a little dot right here. This is the center of rotation. Okay, and then the rotational angle, the angle of rotation is going to be x. See x degrees right here? That is going to be our angle of rotation. Is x degrees. Okay. So this says the image of R is itself, because R is on top of our center of rotation. When you rotate it, it's basically just turning the point around on top of itself. So R does not change. So R prime is equal to R. Okay, and then for any other point, they just used V as an example. If you measure the distance from R to V, or R to V prime, it's going to be the same distance. So if I drew a line from R to U and R to U prime, that would also be the same distance, or R to W and R to W prime, that would be the same distance. And the same thing, if I drew a line from R to U and R to U prime, I'd be making an angle, and they would all be equal to X. They would all have the same angle of rotation. Okay, and then the last thing to remember is rotation is an isometry. This is another word for rigid motion. It means that whatever figure you started out with, you're going to end up with a congruent figure after the rotation. So the rotation does not change any angles or side lengths. Okay, so for example 9, we're going to look at this shape right here, and it calls it a regular pentagon. So regular means that all the sides and angles are congruent. So from P to A, P to E, E to N, N to T, T to A, those are all the exact same length, and all the angles are equal to each other also. Okay, and pentagon means there's 5 sides. So what is the image of E for a 144-degree rotation about X? So it's saying basically if we move the whole polygon 144 degrees, E is going to end up at which vertex? It's going to rotate around to which one of these vertices? Okay, so the center and vertices create so many congruent angles. So if you look at the center, we've got 1, 2, 3, 4, 5 congruent angles. Okay, so if we divide 360 by 5, we can find the measure of each central angle, because this is a whole circle here in the middle, and there's 5 parts to it, so 5 slices of pizza. So if I do 360 divided by 5, we would get 72 degrees. So each one of these measures is 72 degrees. On the back, a 144-degree rotation is 1 times, or how many times the rotation of the measure in exercise C. So if I do 72 times 2, that would give me 144. So I'm going to underline the 2. And 144-degree rotation would move each vertex counterclockwise 2 vertices, because that's how many times we multiplied by. So now what is the image of X for a 144-degree rotation? Or the image of E, around X. So we got to move 2 times. So we're going to go to here, and then we're going to go to here. So E is going to move to A. Now notice I turned in a counterclockwise direction. That was important because it was positive. Okay, so the same type of idea. Hubcaps of car wheels often have very interesting designs that involve rotations. This copied really dark, but I'm hoping you can kind of see. They keep referring to C, M, and Q. M is right, it's written right here in the wheel. So I just drew an arrow. It's the end of this spoke. And Q is the end of this spoke here. C is the very center of the wheel. So it's right here in the center of the hubcap. We want to figure out what is the angle that will move M to Q. So we want to go in a counterclockwise direction, would make us go this way and go around that way. Okay, so the hubcap design has how many spokes? I'm going to start at M and count 1, 2, 3, 4, 5, 6, 7, 8, 9 spokes. So it divides the circle into 9 congruent parts. The angle at the center of each part is going to be 360 degrees divided by 9, which is 40 degrees. As M rotates counterclockwise about C to Q, M touches how many spokes? So it touches 1 here, 2, 3, 4, 5, 6. 6 spokes. So as M rotates counterclockwise about C to Q, M rotates through 6 times 40 degrees, or 240 degrees. The angle of rotation about C that maps M to Q is 240 degrees. Okay, now notice we have an angle bigger than 180, and that is okay. Since we're talking about rotation, we're not actually talking about an angle. Like it doesn't make sense in the geometry we've learned so far to draw a 240 degree angle. So that's bigger than straight. But if we're talking about rotation, you can do that because we can go all the way to 360 degrees in one rotation. Okay, so the rotations we do the most often are 90 degrees, 180 degrees, and 270 degrees. And these are the coordinate rules that are the kind of shortcuts for how to get the answers really quickly. So if you're going to rotate 100 or 90 degrees and you start with any point, we're going to call it AB. To get the point after the rotation, you switch the order. So the A goes to the end and the B goes to the beginning. And you switch the sign on B. So this doesn't mean make it negative, it just means switch the sign. So if it was negative, you make it positive. If it was positive, you make it negative. Okay, 180 degrees, you just switch the sign of both your A and your B. And then for 270 degrees, it's the same as 90 degrees, only you switch the sign on A.